Okay, ladies and gentlemen, in this video I'm going to be talking about how we do very simple energy calculations involving atomic structure. Basically, we'll be discussing C equals lambda nu and E equals h nu and the sorts of calculations you can do with them. They're fairly straightforward, but if you haven't taken physics, then this might take a bit of practice. So I want to just apply a video with some extra practice problems so you can see how these work. All right, the two atomic structure equation formulas that are in the reference table are these two, C equals lambda nu and E equals h nu. So realistically, any calculations that we're being asked to do involving atomic structure are going to come from these. I did show you an additional formula in class that allows us to calculate the energy associated with a particular energy level. Energy level 1, energy level 2, and that's a fairly straightforward formula as well, but you wouldn't be asked to do that on a test situation, so I'm not going over that particular formula here. More letting you know that it's out there, and it's actually a very straightforward calculation. It's very easy to determine the energy of a particular energy level for electrons in an atom. So to get back to this, we've got C equals lambda nu. What do these things stand for? Big thing to realize that C stands for a constant value. It's the speed of light, and it's always going to be this number for our intents and purposes. So when we see C, when we're looking at this formula right here, C is a constant. It's a given. You already know that number. You're not going to be solving for it. It doesn't need to be told to you in the question, but you have enough information because it's a set value. Lambda, what does lambda represent? Lambda represents the wavelength of a wave, and it is going to be measured in meters because the speed of light is measured. This value 3 times 10 to the 8th is the units are meters per second. So the unit for the wavelength, that distance component of speed, is going to be meters. And then nu, this is C equals lambda nu. This is not C equals lambda v. This is not v, this is nu, this is the Greek letter nu. So lowercase letter, it's spelled nu. And nu stands for frequency. The units for frequency are hertz, which are also seconds to the negative first. So it's per second. It's how many times does that wave occur every second. That's what frequency is telling you. And so the unit for frequency is hertz. You can also just simply say seconds to the negative first, and that would be correct as well. So hertz and seconds to the negative first, they mean the exact same thing. And then the second equation that we have is E equals h nu. E equals h nu was an important concept in terms of advancing quantum theory, saying that energy can only exist in these discrete packets and these chunks. And now, granted, these chunks are very small, because when you look at what the component that goes into this particular equation, we've got h, which is a constant, same thing as before. I want to make you very aware of this. H is a constant. It's always going to be this number, 6.63 times 10 to the negative 34th, excuse me, joule seconds, which is a very small number. And so if you multiply this by the frequency, which again we've got nu there, frequency, how often is that wave occurring every second, you're probably going to get something that's, fairly small, right? Because this is a really small number. So our chunks of energy are small, but they're chunks nonetheless. So this is saying that there are essentially only certain, bits and pieces of energy that, or amounts of energy that we can have, which is why we're talking about the energy of a wave, energy of part of a wave. The unit here is going to be joules for energy. Bear that in mind. You can't put kilojoules into this. And again, it goes back to the units that are on our constant. The units on our constant are joule seconds. So frequency has to be in hertz. We need that per second, because if you put seconds on the bottom and seconds on the top, they're going to cancel out. And we want joules here to cancel out with the joules from Planck's constant. The relationship that we glean from these two formulas, C equals lambda nu. Well, C is a constant. It's 3 times 10 to the 8th meters per second. It's not going to change, which means that if I increase either the wavelength or the frequency of a wave, the other one has to decrease, because when you multiply them together, you're always supposed to get the same value. So as wavelength gets larger, frequency gets smaller. The longer the wave, the less frequently it will be occurring every second if the speed is always 3 times 10 to the 8th. And then we look at E equals h nu, the relationship between energy and frequency, because h is a constant, so we're not really looking at its relationship. It's not going to change. This now is a direct relationship, because if I make my frequency larger, if nu is a larger value, and I multiply it by Planck's constant, my E is going to be a larger value. So I have now a direct relationship. As frequency gets larger, energy will also get larger. Energy increases. So some sample problems doing these calculations using these formulas. The yellow light given off by a sodium vapor lamp used for public lighting, that lovely yellow glow that you get in like downtown areas, and especially urban areas, comes from these sodium lamps. It has a wavelength of 589 nanometers. What is the frequency of this radiation? So in pulling the problem apart, wavelength of 589 nanometers, that's lambda. The problem has given me lambda. What is the frequency of this radiation? Well, that's nu. You're looking for nu. So we're going to do, we have an equation that relates lambda and nu, and that's C equals lambda nu. And we can solve for it because C, remember, this is a constant. It's always going to be 3 times 10 to the 8th. So we know this number. We know this number, sort of. And we're solving for nu, well, we can do that. Now, the reason that I mentioned that we know the wavelength, sort of, is because we have an issue right there. Wavelength has to be in meters when you plug it into C equals lambda nu, because C is 3 times 10 to the 8th meters per second. Unit agreement, unit agreement, unit agreement, unit agreement. Units have to agree with one another, and right now they do not. So the first thing that you need to do in this problem is take your 589 nanometers and figure out how many meters that is. It's a simple conversion. Nano is a prefix that you should know. You should know nano. If you don't, go look it up, learn it, get it in your head. You need to know this conversion. You can do this a couple different ways. I'm choosing to do it this way. 1 nanometer is 1 times 10 to the negative 9th meters. You could also say that 1 meter is 1 times 10 to the 9th nanometers. That would be inverted. The 1 times 10 to the 9, not negative 9, would be on the bottom and 1 would be on the top. Either way, they're saying the exact same thing. Nanometers cancels out. I'm converting my nanometers into meters. When you do this math, which hopefully you can do without a calculator, 5.89 times 10 to the negative 7th meters. And this is the lambda that we want to plug in because the units are now agreed. And we can do that now. It's a fairly straightforward calculation at this point. 3 times 10 to the 8th meters per second is equal to the lambda value, which is 5.89 times 10 to the negative 7th meters times the frequency. And when you're doing this with your calculator, please watch parentheses around values that are in scientific notation. Otherwise, the magnitude, I'm sorry, the number in your answer will be correct, but the magnitude will be significantly off. Basically, the exponent on your 10 will be way off. So be very careful when you're doing this math. Divide both sides by 5.89 times 10 to the negative 7th meters, and you get a frequency of 5.09 times 10 to the 14th hertz. Hertz is the unit for frequency. You could also say that same value seconds to the negative first, because it means the exact same thing. So that's one problem. Second problem, what wavelength of radiation has photons of energy 5.44 times 10 to the negative 18th joules? Okay, second problem. Figure out what the problem's asking, what information it gives us, and figure out how to get from point A to point B. First up, what information does the problem give us? Energy of 5.44 times 10 to the negative 18th joules. Right in it there, the problem has given us energy. That's going to be our starting off place. Starting off point, 5.44 times 10 to the negative 18th joules. It is asking what wavelength. Wavelength is lambda. That means that we're trying to calculate lambda. We go to our reference table and we realize we do not have a formula that directly relates energy and wavelength. So what are we going to do? Start with the number that the problem gives you. Think about what you can do with this. We have a formula that involves energy. E equals h nu. Think about this. This was given in the problem. E was given. What do we know about the other components? H, that's a constant. That's always going to be the same number, which means that if I'm looking at E equals H nu, I have energy and I have Planck's constant. I have those two numbers. This means that I can solve for nu. I can solve for nu. I have enough information to solve for nu. What good is that going to do me? Think about it. I'm trying to get wavelength up here. We have a second equation that says C equals lambda nu. Second equation that says C equals lambda nu. Now, I do not have nu provided to me in the problem, but I can calculate it. If I calculate nu here, I can then plug it in here, and I'll have that nu value there. Why is that useful? Because C is a constant. I always have that number. It's always 3 times 10 to the 8th meters per second, which means that I know this, and I know this if I've already done that math from E equals H nu, and that means that I can solve for wavelength, which is what the problem, precisely what the problem is asking me to do. So again, this is a two-step process. Physics people, if you want to jump right into E equals hc divided by lambda, you may do that, but I'm showing the derivation of that. This is a two-step process. We use the first equation, E equals H nu. We solve for nu. We take that nu value, we plug it in into C equals lambda nu, and we can solve for the wavelength. So that's exactly what we're going to do. We're going to take our energy, 5.44 times 10 to the negative 18th joules. We're going to set it equal to Planck's constant, 6.63 times 10 to the negative 34th joule seconds times nu. You solve, divide both sides by Planck's constant. We get a nu value of 8.21 times 10 to the 15th hertz. This is not our answer, but it's very useful information. It's along the way to getting our answer. So this is part 1. Part 2. I'm now going to take that value that I calculated for nu, and I'm going to use C equals lambda nu. C is 3 times 10 to the 8th meters per second. Lambda, that's what we're trying to calculate. Nu, what's nu? Oh, we just figured that out. 8.21 times 10 to the 15th hertz. Divide both sides by the frequency, and we get a wavelength of 3.65 times 10 to the negative 8th. Units, what's the unit on wavelength? Meters. And that's our final answer. So it's important to realize that I only need to give you energy, and then I can directly ask for a wavelength. You're just using the combination of these two formulas. You're utilizing the fact that nu pops up in both of them, and therefore you're using nu as the intermediate, as an intermediate step. If I give you energy, you calculate nu, and then you use nu in C equals lambda nu to get wavelength. That's the relationship there. So I hope this helps when we're looking at some of the homework problems, because that's what you're going to be doing in a lot of the Chapter 6 homework problems, practicing working with these equations. And if you have any questions, please do not hesitate to see me.